All right, good morning. I'm going to start a couple minutes early so I can do my habitual checking to make sure the internet still works thing. Oh, interesting. I can see YouTube is good. I am waiting to make sure that Twitch is online, but I'm watching an ad for Nerf guns because apparently that's what targeted advertising thinks I want to know about today. Yeah, good morning, everybody. Or I guess a lot of folks aren't in a time zone where it is morning for them, so good day, I suppose, is a little bit more general. We're jumping back into speech and language processing, and I'm gonna wait another minute before I get going so that folks who are going to appear exactly at 9 won't be surprised. Last week, 2 weeks ago, in the past, before this was a regular thing and I knew when I was going to be doing it, there's the monitor. Now I can hear me. Good morning, Jath. Oh, thank you for sharing that, the link on standard notation again. That was very helpful. Anyway, the last time that we did this, which was in the past. Good morning, Akraf? Atraf? Hard to tell. Sorry about that. I apologize for saying your name wrong, probably. We read the first half of this chapter, where we learned all about the architecture of neural nets, specifically multi-layer perceptrons. We learned about why that's a little bit of a misnomer, but it's what we call them. But what we didn't talk about was how to train them. We talked about the architecture, we talked about activation functions, we talked about weights, we talked about the graph structure, we talked about some of the basic notation, and now we're going to actually talk about the training. And it is 9 o'clock, so let's get going, because I'm guessing that this one, we're about halfway through, so we might finish the chapter today. But I'm guessing that we're going to get into a little bit of the slower going here. So, a section 7.4 of the 3rd edition of Speech and Language Processing by Jurafsky and Martin. A feed-forward neural network is an instance of supervised machine learning in which we know the correct output y for each observation x. So that is the definition of supervised machine learning. It is not the definition of a feed-forward neural network. What the system produces via equation 7.12 is y hat, the system's estimate of the true y. The goal of the training procedure is to learn parameters wi and bi for each layer I that makes y hat for each training observation as close as possible to the true y. So wi was what we were using for the weights, which is a matrix of values, and bi is what we were using for the bias, which is a vector, maybe. Or is it a fixed term for each layer? I think it's a fixed term for each layer. We'll go back to it if it comes up again. In general, we do all this by drawing on the methods we introduced in Chapter 5, which we haven't read, for logistic regression, so the reader should be comfortable with that chapter before proceeding. First, we'll need a loss function that models the distance between the system output and the gold output, and it's common to use the loss used for logistic regression, the cross-entropy loss. So these are new concepts in this chapter. Second, to find the parameters that minimize this loss function, we'll use the gradient descent optimization algorithm introduced in Chapter 5. There are some differences, so we're not just going to use vanilla gradient descent. Third, gradient descent requires knowing the gradient of the loss function, the vector that contains the partial derivative of the loss function with respect to each of the parameters. So the gradient is basically describing the shape, you can think about it like the 2-dimensional or 3-dimensional shape of the space that we're exploring blindly. Here is one part where learning for neural networks is more complex than for logistic regression. I think logistic regression might be a typo, and I'm actually going to make myself a little note to email the authors and let them know about that, because that's what good beta readers do. I am not an invited beta reader. I just want to read it. what page is this? Page 10. Page 10, chapter 7, logistic regression. All right. In logistic regression, for each observation, we could directly compute the derivative of the loss function with respect to an individual w or b. So it's easy to sort of see the shape of the space around us, because it's usually two-dimensional or three-dimensional. But for neural networks with millions of parameters in many layers, it's much harder to see how to compute the partial derivative of some weight in layer 1 when the loss is attached to some much later layer. How do we partial out or parcel out? I don't know that that is an error, but it could be. So I realized last time as we were reading that I didn't actually make note of any of the typos that we found. How do we partial out the loss over all these intermediate layers? So rather than sort of moving one value and then you can immediately see the direct impact of that on something else, this is like you walk up to a spider web and you want to move that corner of the spider web, 1 inch. A spider web floating in space that's semi-rigid, I guess. So you tug on something in the spider web, but you can't tug on like the corner you want to move. You have to tug on something else, and that has other effects that sort of like ripple out through the spider web that you also have to account for. The answer is the algorithm called error backpropagation or reverse differentiation. Backprop. I'm trying to find, what's the word for that? Like collegially, the cutesy nickname is backprop. All right. Adita says it may be the partial derivative. It could be, yeah, but it could also be parcel. Like they both make sense. Yeah. And Jayanth says, seems like an accepted mathematical term. First time I'm hearing it. Me too. I will admit that my math background is sort of autodidactic and splotchy. I've done a lot of teaching myself math, and a fair amount of formal instruction in statistics, but less formal instruction in like mathy math. All right, loss function. The cross-entropy loss that is used in neural networks is the same one we saw for logistic regression. In fact, if the neural network is being used as a binary classifier with the sigmoid at the final layer, the loss function is exactly the same as we saw with logistic regression in equation ? Presumably in chapter 5. So the loss CE of y hat and y is the negative log probability of y given x, which is the negative of y times the log of y hat plus 1 minus y times the log of 1 minus y hat. I leave this reading chapter 5 as an exercise to the reader. I don't know, maybe we'll read that next. What about if the neural network is being used as a multinomial classifier? Let y be a vector over the C classes representing the true output probability distribution. The cross-entropy loss here is LCE of the loss. What is E? I don't know what E is. Did we talk about that in here when we were talking about formalizations? We did not. Oh, it's the cross-entropy loss. Excellent. Sorry, I was confused because here we talked about C being classes, and I was like, wait, is this the loss of classes across some value E? No, it's just the cross-entropy loss. Figured it out. Of y hat and y is the sum across all classes the negative summation across all classes of y times the log of y hat. We can simplify this equation further, assuming this is a hard classification task, meaning only one class is the correct one, and that there is another output unit in y for each class. Sorry, there was no that in that sentence. Assume this is a hard classification task, meaning there's only one class is the correct one, and that there is one output unit in y for each class. If the true class is I, then y is a vector where yi equals 1 and yj equals 0 for all instances such that j does not equal I. So when I and j are different, and j is, I don't know where we've gotten j from either. Oh, I'm so sorry. I can't read characters very well, but somebody says I really like this. I'm glad. Thank you. All right. A vector like this, where one value equals 1 and the rest is 0, is called a one-hot vector. Oh, this is just the mathy way of saying one-hot encoding. So if you had like a column that has whether an animal is a cat or a dog, you can turn it into two columns where one column is cat and the second column is dog. And instead of saying cat or dog in the column, you can say 0 if it's not a cat in the cat column and 1 if it is a cat in the cat column. All right, I got this. I'm picking up what he's putting down. They're putting down, sorry. All right, now let y hat be the vector output from the network. Okay, so when we have the final output layer, we get out a vector of probabilities where a probability is assigned to each class. So it'll be a vector that sums to 1. I do remember this. The sum in equation 7.4 will be 0 except for this true class. Hence, the cross-entropy loss is simply the log probability of the correct class, and we therefore also call this the negative log likelihood loss. So if I say there's a 5% probability that it's in the right class, it doesn't matter what probabilities I assume to any of the other classes, my loss will be 0.5, more or less. So it's just like, how much probability did you assign to the correct class when you were finished with your model? Does the loss function work if we have more than 2 classifications? This one won't, because it is for a single class classification. I think we talked about it, blah, 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 up here in the loss functions section. Cross entropy loss, and then we talked about, yeah, so we've only talked about binary classification so far, with the sigmoid at the final layer. Yeah, that'll be a different loss function. Good call. All right, blah, blah, blah. The sum of equation 7.14 will be 0 except for the true class. Hence, the cross entropy loss is simply the log probability. Oh, I already read that. All right. Plugging in the Softmax formula from equation 7.1 in the last section with k, the number of classes. Okay, so we've got k classes. So the cross entropy loss of y hat and y is the negative log of e to the zth power summed over k to j minus 1 times e to the zj sub j power. Adita says, but 7.14, so C classes indicating more than 2 classes, right? Yes. Yes, so the binary, yes, you're right. So the binary classification here is a characteristic of the final layer. So the output will be the probability that it is assigned to a specific class for each node in the output layer. Yeah, you're right. And then this portion starting from 7.14, no, starting from 7.15 is for hard classification, so only one class is the correct one. Yes, good call. Thank you. Yes, so you could use just regular cross entropy loss for multiclass. Idea says 7.3 is for binary. Y given x. Possibly? Maybe yes? Yeah, because it's only for one class because we're not summing across multiple classes. So correct again. Yeah, so I think regular cross entropy loss will work for multi-class classification. Let's actually, you know what? I have the power of a search engine at my fingertips. I'm gonna use Google. You could use whatever search engine you like. Cross entropy loss multi-class data science stack exchange multi-class classification from Princeton CS. I think that Princeton CS is probably a pretty good source. Let's try multi-class. Oh, that's not gonna be helpful because that's the title of the lecture. Cross entropy. Blah blah blah. The hypothesis class for multi-class logistic regression. Softmax on linear transformation. It can be used to derive the negative log likelihood cross entropy. Cross entropy for conditional distribution. So the P probability of y given x part here before we make it the negative log likelihood. So just the regular likelihood denotes the empirical distribution of the data. Yx? Yes, okay. And then negative log likelihood is the cross entropy between the data and the model output, which is some constant minus. So KL divergence is the difference between some constant minus the cross entropy. Yes, so this is a distribution across all classes and is not necessarily binary. So where the multi-class classification comes in is in the probability distribution. Well, that seems right. Maybe. It's been a really long time since I talked about cross entropy, or since I studied cross entropy. And by a really long time, I mean like 2 years? 2.5 years? Closer to 3. Woof. Yeah, let's come back to that. So we had gone through 7.16 was the last equation we looked at. So some loss function, in this case, negative log likelihood. Computing the gradient. So the gradient, we're going to have to compute the gradient regardless of what loss function we use. How do we compute the gradient of this loss function? Computing the gradient requires the partial derivative of the loss function with respect to each parameter. For a network with one weight layer and a sigmoid output, which is what logistic regression is, we can simply use the derivative of the loss that we used for logistic regression in equation 7.17 and derived in section, question mark. Okay, so we have a very simple loss space to explore, and we can just look at the gradient using the partial derivative. Oh, no, the plane derivative. Or for a network with one hidden layer and softmax output, we can use the derivative of the softmax loss from equation, presumably also in chapter 5. This part here is very much in concert, in dialogue with a piece that we have not read. Okay, so backwards 6. Is that gamma, maybe? Let's see if I can find Janth very helpfully posted a link to notation. I know it's a Greek letter. I don't think it's beta. Greek letters. I can't just call it backwards 6. I know it has a different name. There we go. Help me out, Wikipedia. Do any of these look like a backwards 6 to y'all? Nope. Delta. Does that look like a delta? That looks like a weird delta. That could be delta. Yeah. Does anything else look more like that? No. Let's call it delta. Okay. So the delta of the cross-entropy loss, Erica says that's the notation for partial derivative. It's delta. Thank you, Erica. There's a little bit of a lag between when you say things and when I actually see things, so I do still very much appreciate your comments. I was not ignoring Erica. All right, so delta of the cross-entropy loss divided by the weights of k, and k is... Where do we get k from? It's a mystery. Oh, it's called dough, apparently, Jan says. Thank you. You guys are so helpful. And Sharam also sent a link to Delta page on Wikipedia, which I appreciate. I still don't know where K comes from. It's not here. Well, maybe that's the constant. So the log loss is 1 squiggle. I don't know any of this notation. I'm so sorry, guys. Curly braces y equals k minus the probability of y equals k given x times x sub k. I have no idea what we're talking about here. I don't know where k is coming from. I don't know what the curly braces mean. That's a mystery to me. Well, this is clearly a reference to something from a previous chapter we haven't read, so I'm just gonna skip ahead a little bit, and we can come back to this at a later time. Also, maybe we should have read chapter 5 first. But these derivatives only give correct updates for one weight layer, the last one. For deep networks, computing the gradients for each weight is much more complex. Since we are computing the derivative with respect to weight parameters that appear all the way back in the very early layers of the network, even though the loss is computed only at the very end of the network. So it's sort of like a game of telephone. Adita says it's an indicator function. Galva also says it's an indicator function. Michael Thomas says 1 squiggly brackets is like a counter. You know what I wish? I wish that this were in code rather than mathematical notation. Okay, I'm gonna read about indicator functions now. Because if I don't know, also other people don't know. All right. In mathematics, that is what I'm interested in, an indicator function, or I'm on Wikipedia now, a characteristic function is a function defined on a set X, is that where X came from? That indicates membership of an element in a subset A of X having the value 1. Oh, it's one hot encoding. JR says K means the class. It is a notation for an indicator function. Okay, so we're basically just one hot encoding, and then we're subtracting the probability that y is k given x, and x is the something. Did we ever figure out where x came from? Did I remember where x comes from? That's the question. K given x, x sub k. I don't know. Still don't know where k comes from. But basically we're doing one hot encoding, and we are taking the ground truth and subtracting the probability that we got it right. And then we're multiplying that by x sub k, which is something. It came from somewhere. Presumably it came from chapter 5. And if I'd read chapter 5 like someone who reads a book the normal way from back to front, nope, that's the wrong way to read a book from front to back. I would have better foundation here. Yeah, so we're just looking at how wrong we are for each data point, and then using that, taking the derivative of that to figure out how we should change our weights. Maybe x is the weights? JR says, means the probability that the class came from the parameters. Okay, that makes sense. So the came from the parameters of our model. yeah, so it's just describing, it's very like the, it's very like logistic regression, but again, I don't know what the math symbols mean. I don't know all of them, guys. I'm sorry. And it's one of those things where I know a lot of these things are conventional. So yeah, of course, everyone knows X sub k is, you know, the Dairy Queen at the corner of Frosty and ice cream or whatever. That's not what it ever means. But these conventions that, again, I just don't have as much exposure to. All right. But I think I have an okay intuition of what's going on here. Could I derive this? No, I couldn't. But that's okay. That's why we have classes that do it for us. Galva says, I think I get it. Y is the predicted class. Yeah, I think so. So this is the correct answer, and this is our guess. More or less. But this will only work for the last layer of the network, and it won't update. It won't tell us the correct direction to update earlier layers. So to do that, we need to use backpropagation, or backprop. Rumelhart et al. 1986. Oh, this algorithm is older than I am. Well, backprop was invented specifically for neural networks. Especially for neural networks. It turns out to be the same as a more general procedure called backward differentiation, which depends on the nation of computation graphs. Let's see how that works in the next subsection. So, the idea of section 7.4.2 are here are some things that nobody uses with deep neural networks because they don't work. So we're going to do something different. Computation graphs. A computation graph is a representation of the process of computing a mathematical expression in which the computation is broken down into separate operations, each of which is modeled as a node in a graph. What is the difference between a computation graph and an abstract syntax tree? If they are the same, then this will be a great time saver for me. These may actually be different things. So abstract syntax tree is if you're doing a line of code, it basically figures out the order of operations and the hierarchical relationships between things in your command and passes it to the compiler, maybe. I don't know. Do I have a CS degree? Nope. All right. And then if we look at for AST in here, are we still in abstract computation, dynamic computation graphs? A dependency graph of inputs and output operations also appears within abstract symbol trees, AST, which are some of the most progressive compilers construct during the interpretation of the source code structure. The AST is then used to generate assembler instructions or machine instructions in the process of linking with libraries and forming an executable. The AST is a directed graph that represents the structure of the data, operations performed, and the control flow specified by the source code. Dynamic computational graph framework, unlike with switch case statements or intermediate AST models and compilers, one can manipulate the operations, optimize them, tune them. Okay, so when AST is generated and then it's static and a computational graph can be edited, is what I got from that. JR says, automatic differentiation is how TensorFlow does gradient descent by example. There are nice explanations in Geron's book. Oh, thank you. Perhaps we will read that in the future. So it looks like ASTs are a subset of computation graphs, maybe? All right. Blah, blah, blah. Separate operations, each of which is modeled as a node in a graph. This is the worst way to show what a tree is. Sorry. Consider computing the function LABC equals C times A plus 2B. If we make each of the component addition and multiplication operations explicit and add the names D and E for the intermediate operations, the resulting series of computations is D equals 2 times B, so this term is turned into D. E equals A plus D, so A in our input and D that we've generated is a medial thing. And then L equals C times E, E being the a plus 2b part, and then c being the c that we got from the input. So we've created sort of intermediate terms. We can now represent this as a graph with nodes for each operation and directed edges showing the outputs from each operation as the inputs to the next, as in figure 7.9. There we go. This is a much nicer way to show a tree structure rather than a series of equations. Okay, so it's a forward pass. We go this direction. If our inputs are A is 3, B is 1, C is -2, then we can compute D by multiplying B by 2, and the output of that is 2, and then we get past, that gets passed to E, which is our next intermediate term. And then A, which we were given in the input, E equals D plus A, 3 plus 2 is 5, and then L equals C times E. C is -2, E is 5, so L equals -10. So it's just sort of a graph structure that shows us how to do the things and the order of operations and what goes into what. This I'm very familiar with. This is home territory for me. This is like Linguistics 101, believe it or not. All right. The simplest use of computation graphs is to compute the value of the function with some given inputs. In this figure, we've assumed the inputs A equals 3, B equals C, and B equals 1, and C equals -1. And we've shown the results of the forward pass to compute the results L, 3, 1, 1, and 10. -10. -10. That's definitely a typo. I'm going to make a note of that. -10. And that is on page 12. All right, the forward pass of a computation graph, we apply each operation left to right, passing the outputs of each computation as the input to the next node. So we could also do this, if this were a deep learning graph, this would be the output layer, this would be the input layer, and these would be some hidden layers, and it would be much more complex. All right. Backwards differentiation on computation graphs. The importance of the computation graph comes from the backwards pass, which is used to compute the derivatives that we'll need for the weight update. In this example, our goal is to compute the derivative of the output function L with respect to each of the input variables, E. Someone said dou rather than delta, so I'm going to say either dou or delta. I'm not sure which one is more canonical. Or maybe do you say like the derivative of L over A and the derivative of L over B and the derivative of L over C? I don't know if that's right, but that's how I'm going to say it. The derivative L over A with little delta does tells us how much a small change in A affects L. Backwards differentiation makes use of the chain rule in calculus. Oh, I took calculus a really long time ago, and I don't remember most of it. Suppose we are computing the derivative of a composite function, f of x equals u of v of x. The derivative of f of x is the derivative of u of x with respect to v of x times the derivative of v of x with respect to x. So df over dx equals du over dv times dv over dx, and we... Oh, I can't see both of these things on the same screen. Dou L by dou C, Michael says. Thank you, Michael. That's very helpful. Oh, and Michael also said earlier, kth class of the C classes, which I did not notice, and I apologize. Dou L by dou C. And now we can all say math words better. But this one's not dou. This is just D. Because I'm guessing that it's not over a class of things or a set of things. What was I doing? This one I probably think is probably a better example. The chain rule extends to more than two functions. If computing the derivative of a composite function f of x, so here's our f and here is our x, our function and our input, equals u of v of w of x, the derivative of f of x is u over v, so u over v from our first two nested functions, and then v over w for our inner nested functions, and then w over x from our last set of nested functions, and then those are all multiplied by each other. Let's now compute the three derivatives we need. since in the computation graph L equals CE, we can directly compute the derivative dou L by dou C. Thank you, Michael. Dou L by dou C equals E. For the other two, we'll need the chain rule. And this that we're talking about here comes from this dude here. This little computation graph we constructed earlier. So we are chaining these things together. So LCE. So LCE is the final function that we have. And this is, if we're doing a forward pass, there's only one set of nested functions. So dou L by dou C is E because this is within this function. I'm pointing to the screen. That's not helpful. You can't see my finger. For the other two, we'll need to use the chain rule. So dou L by dou A equals dou L by dou E by dou A. So dou L of dou A. So we want to know the relationship between A and L. And we can do that, but in the intermediate here, we have this E term. So L of A is L of E, which is in the medium in the middle here, and then E of A. So we're sort of going back and treating each of these like a nested function. And then we do that for all of those. Equation 7.22 thus requires 4 intermediate derivatives: dou L by dou E by dou A, dou E by dou D, and dou D by dou B. And I have reached semantic saturation, and dou sounds like nothing now. I'm assuming it's dou and not do. I don't know why I'm assuming that, but that's what I'm going for. Which are as follows, making use of the fact that the derivative of a sum is the sum of the derivatives. So we know what the sums are. We know what the derivatives are because we know the sums. And we know those because we have passed in numbers. No, this should hold across. Galva says, wait, I've never heard it as dou, but rather D. Oh. See, this is why reading math aloud is danger zone. I don't know, is it dou or D? Name of lowercase delta. Is the fourth letter. Okay, yeah, no, but how do you say it? How do you, is it dou or is it? I want to know the name. If I look for how to pronounce D-O, it's going to tell me to pronounce it do, because that's how the internet works, and frequency is important. If anybody knows, let me know in the chat, and then we can say it correctly, I think. Plus dou, maybe? Michael says it's not delta. So is it dou because it's across the set of all possible inputs? Because this one's definitely D. This one I'm very comfortable with saying it's D. And Erica also says dou is different than delta. Thank God there's math people here. Pronounce dou, Greek letter. Epsilon. What? What? Okay, this is a knowledge graph failure. This is not how this should go. What do Greek letters mean? It depends. If any non-Greek scholar attempts to pronounce the classic texts in the ... I don't want to know. The table gives Greek letters, their names, equivalent English letters. Mohammed says D. D-E-E. So it would be like dl by dc or dol by doc. Well, regardless, the sort of like underlying idea should be the same, and it just makes me sound uneducated. And that's fair because I have, as I said, fairly limited formal math education, which I'm rectifying now. Okay. Calculus. Let's keep going. And yes, we'll come back to this if we need to. In the backward pass, we compute each of these partials along each edge of the graph from right to left. Michael says, try Googling partial derivative. That makes sense. D-E-R-I-V-A-T-I-V-E-S. The partial derivative of a function of several variables is a derivative with respect to one of those variables, with the others held constant, as opposed to the total derivative, in which all variables are allowed to vary. Variously denoted by f prime x, fx, this dude, the backward 6 that we still don't know how it's said, Nivaditha, sorry about that, says that it looks like D is commonly used and has helpfully provided a link to this question where someone is asking exactly the question that I have. I'm not an English speaker, that is why I asked that question. Buddy, I am an English speaker and I also don't know the answer. So this one has said D. This question is not about mathematics. Within this, it's definitely about mathematics. You're being a little bit of a butt. So this person says, I say it D. I pronounce it D. Very occasionally del. Del. So it's del rather than do? What's the difference? Oh wait, but this person says day? What? Del means something different. Okay, so it's not del, and that has a lot of upvotes, so probably del isn't the one. So maybe day? This has 2 upvotes. I still don't know what the letter's called. So people would say day or do, and this is for 5, which is the one that we want. Is it the fact that it's to the 3rd power? Galva says lol day. Let's call it D. Let's call it fancy D, and that's what we're gonna call it. Ugh. Yeah, good enough. This is the problem that happens when you do not have a lot of lecture experience, and also you read papers by yourself quietly. It's the math equivalent of thinking that I didn't know that pneumonia and pneumonia were the same disease until I was in like 8th grade, because I had read one and heard the other and had never like linked that those 2 words were the same word. Yeah, let's call it D. Nobody says, so del is the one that people don't say. At least some people in the chat say do, or maybe do. And also some people say day. But del is something different. So del is delta. Regardless, we're getting way off track, and I haven't had my second coffee, so I am probably more easily distractible than I would be otherwise. All right, blah, blah, blah. Backwards pass. We compute each of these partials along each edge of the graph from right to left, so forward, backward, multiplying the necessary partials to result in the final derivative we need. Thus, we begin by annotating the final node with dl by dl equals 1. Moving to the left, we then compute dl by dc and dl by de and so on until we have annotated the graph all the way to the input variables. And then there's a figure of them doing that. Oh, okay. Yeah. So it is, these are the numbers where I was like, where is 1 coming from? Does that hold for everything? This is coming from the numbers that we're putting in. E of A, E of T is 1. Niveditha says, or partial D would work too. So like partial E by partial D? Maybe? We'll figure it out. I'm sure you guys will let me know if I'm doing something humorously incorrect. Blah, blah, blah. And we've animated the graph all the way to the input variables. So here, we can calculate the partial because we have the input variable. The forward pass is conveniently already will have computed the values of the forward intermediate variables we need, like D and E, to compute these derivatives. Okay, so we do need the values to compute the derivatives. That was my question. Can we do it as just like a system of equations and then plug in our... I mean, we can. Yes, that is the answer. Yes, we can do it as a system of equations, but we won't know what the value is until we have the variables. Figure 7.10 shows the backward pass. At each node, we need to compute the local partial derivative with respect to the parent, multiply it by the partial derivative that is passed down from the parent, and then pass it on to the child. All right, so the parent node here, usually the parents are at the top, would be L, and then these would be child nodes, but the direction of movement is this way? I'm a little bit confused by parent-child here. VG or Vijay, maybe? The symbol referred to as del, 5, not to be confused with delta, also known as del. Are you kidding me? D, partial, especially in LaTeX, round D, curly D, doe, die, or dabba. Thank you, that was very helpful, but I'm sad on the inside that these are the conventions. Oh. All right. Let's call it D because that seems the least confusing. So that's my convention. I'm picking one. I'm going with D. I love that there's 80 names for the same thing. I love that some of the names are the same things as the other things. And from Wiki, it looks like del and doe are both okay. I'm going to go with D. I'm doing it. I'm picking that. I'm just going to go with D. And hopefully I won't get yelled at. No, I don't think you guys will yell at me. Y'all are great. All right, back to the backward pass, and then I'll say names of things when they come up again. Okay, so at each node, we must compute the local partial derivative with respect to the parent, multiply it by the partial derivative that's being passed down from the parent, and then pass it to the child. Yes, okay, yes, because we're using the chain rule, this has to be the parent, even though it's the cell that everything else is feeding into when we're going backwards. So in neural network, the output would be the parent for doing the chain rule. Which, yeah, I guess we've switched, because when we were talking about connections, yeah, we did where up was the output layer and down was the input layer, and now we have switched from going to right to left, which is fine. I just have to reorient. Let's go all the way back down. Of course, computation graphs for real neural networks are much more complex. Figure 7.11 shows a simple computation graph for a two-layer neural network with n sub 0 equals 2, n0 equals 2, n1 equals 2, and n2 equals 1, assuming binary classification and hence using a sigmoid output unit for simplicity. The weights that need updating, those for which we need to know the partial derivative of the loss function, are shown in orange. So when I was just talking about when we were, let me zoom in a little bit, it's a little bit small actually. Oh wow, it's actually really quite small. Let's make it a little bit bigger. So when we were looking at the graph up there where the output was the top and the input was the bottom, now the output is the right. I'm fairly sure that's the right side, and the input is the left. So we are not tuning this bias, but we are tuning this bias. I'm assuming this is an error and we do want to tune the bias term as well for this cell Z1. So what we need to compute is the bias for each layer and also the weights for each layer as we go down through the network. Yeah, okay, that's actually fairly straightforward for me at this point. I was looking at that graph and I was like, it's too scary. But I think that B1 in the first layer should also be orange, and I will make a note of that. Layer, and we are on page something or other. Page 14. I mean, it's very possible that there's empirical results that shows that not tuning the bias in one cell in the input, the first hidden layer, is a good idea that I just don't know about, but it seems unlikely. I could be wrong, but it seems unlikely. Figure 7.11. All right. In order to do the backward pass, we'll need to know the derivatives of all of the functions in the graph. We already saw in section the derivative of the sigmoid sigma, d sigma of z over dz equals sigma z times 1 minus z. We'll also need the derivatives of each of the other activation functions. The derivative of tan is d tan z over d of z is 1 minus tan squared of z. The derivative of the ReLU is d of ReLU z over dz is 0 when x is greater than 1, and 1 if x is greater than or equal to 0, because it forces things to 1 or 0 with a sharp line in it. Rather than a sigmoid, which is a nice, like, whoa, it's a nice swoopy. You can be, you know, a number of values. All right. More details on learning. We have read 0.5 sections. No, we've read 5 subsections. Optimization in neural networks is a non-convex optimization problem, more complex than for logistic regression, and for that and other reasons, there are many best practices for successful learning. So in logistic regression, if you look at sort of like the space of the errors that you can make and the adjustments you can make, there is like one good solution. It's, you know, I'm making shapes with my hands, and you can't see the shapes I'm making with my hands, and I know this, and I keep doing it. So there's a low point that you can find and hang out and be like, oh, I found the local minima. But for neural networks, the shape is bad. It's not bad. It's just a weird shape. Like, what's the local minima in a, what are those bases that like fold inside themselves that are non-Euclidean or whatever? Euler bases? Euler bases? Anyway, where's like the low point on that? It's harder to say. All right. For logistic regression, we can initialize gradient descent with all weights and biases having the value 0. In neural networks, by contrast, we need to initialize the weights with small random numbers. It is also helpful to normalize the input values to have 0 mean and unit variance. So you have a mean around 0. And I think I have read some papers that suggest that if you are going to, if you're initializing randomly, you do want to have a distribution of random initializations that are based on some function of your data, which I think is what the unit variance is. Maybe. But I also read those like 2 months ago, so who knows if they're still current. Various forms of regularization are used to prevent overfitting. One of the most important is dropout, randomly dropping some units and their connections from the network during training. Hinton and Srivastava, Hinton et al. 2012 and Srivastava et al. 2014. Hyperparameter tuning is also important. The parameters of a neural network are the weights W and biases B. These are learned by gradient descent. Okay, so the first, that bias that's not blue should definitely be orange. That is blue should be orange. We do want to update all the biases. The hyperparameters are things that are set by the algorithm designer and not learned in the same way, although they must be tuned. Hyperparameters include the learning rate nu I think that's a new. The mini batch size, the model architecture, the number of layers, the number of hidden nodes per layer, and the choice of activation functions, how to regularize, and so on. Gradient descent itself also has many architectural variants, such as Adam, Kigma, and Ba 2015. So these are sort of qualities of your model, not things that are learned. Finally, most neural networks are built using computation graph formalisms. Finally, most modern neural networks are built using computational graph formalisms that make all the work of gradient descent computation and parallelization into vector-based GPUs, graphical processing units, very easy and natural. Michael says EDA. It wasn't new. This is EDA. Thank you, Michael. PyTorch, Paszik et al. 2017, and TensorFlow, Abadi et al. 2015 are two of the most popular. The interested reader should consult a neural network textbook for further details. Some suggestions are at the end of this chapter. So this is like, these 4 paragraphs are like all of the practical advice in terms of network structure that we've gotten so far. No, that's not fair. We don't have actually a lot of suggestions in terms of network structures to use, just that they are things that can be tuned. I'm waving my hand around, and again, you can't see it. I'm sorry. I need to stop making hand gestures. All right. Neural language models. Oh, finally, we're to the language modeling part. Our first application of neural networks, let's consider language modeling, predicting upcoming words from prior word context. So if I said peanut butter and, a good neural network might suggest, a good language model might be like, oh, banana, jelly, pickles. I really like peanut butter and pickle sandwiches. They're a family favorite. So deducing what the next word is going to be. Neural net-based language models turn out to have many advantages over the n-gram language models of Chapter 3. Among these are that neural language models don't need smoothing, they can handle much longer histories, and they can generalize over contexts of similar words. So smoothing is the fact that because most words are very rare, you're not going to see most words next to each other, so you need to add a little bit of fuzziness to your error term so that you can predict very rare things. N-grams, people don't go much above 5, which is modeling language as the set of 5 words that occur next to each other, and like all set of 5 words that you see next to each other. And if you're remembering all of them, then being much bigger than 5 can quickly explode your storage memory. It's a lot to remember in the computer. Oh, sorry, this is earlier than I usually stream, and I can tell the difference. I don't know if you can. And they can generalize over context of similar words, so you can more easily incorporate things like vector space similarity for semantic measures. For a training set of a given size, a neural language model has a much higher predictive accuracy than an n-gram language model. Further, neural language models underlie many of the models were introduced for tasks like machine translation, dialogue, and language generation. We didn't read the n-gram chapter, but n-grams I'm very comfortable with. On the other hand, there is a cost for this improved performance. Neural net language models are strikingly slower to train than traditional language models, and so for many tasks, an n-gram language model is still the right tool. In this chapter, we'll describe simple feed-forward neural language models, first introduced by Bengio et al. 2003. Modern neural language models are generally not feed-forward, but recurrent, using the technology that we'll introduce in Chapter 9. So we're not in our neural network architecture, we just go from the beginning to the end. There's no sort of like cyclical structures. A feed-forward neural language model is a standard feed-forward network that takes as input at time t a representation of some number of previous words, wt-1, wt-2, etc., and outputs a probability distribution over possible next words, and it's usually determined based on your some sort of lexicon that you're using. Thus, like the n-gram language model, the feed-forward neural language model approximates the probability of a word given the entire prior context, p of wt given p of 1, p summed over t minus 1 to 1, by approximating based on the previous n words, the n previous words. So the probability of word t given word t minus 1 is approximately the probability of word t given word t minus 1 to word t minus n plus 1. In the following examples, we'll use a 4-gram example. So we'll show a net estimate. So we'll show a net to estimate the probability p of wt equals I, wt minus 1, wt minus 2, wt minus 3. So I give you 3 words and ask you to guess what the 4th one is. And for training, I give you a set of 4 words. Okay, embeddings. In neural language models, the prior context is represented by embeddings of the previous words. Representing the prior context as embeddings rather than by exact words as used in an n-gram language model allows neural language models to generalize to unseen data much better than n-gram language models. So embeddings are words that are used more together, are in the same context, are closer together in some sort of multi-dimensional space that you train. So you would expect to see things like cat and dog close to each other, and things like cat and, I have to think of a word that's very unlike cat, disestablishment, to be pretty far apart from each other because they don't tend to be used in the same context. So it's just a efficient mathematical representation of that captures some aspects of meaning, we think. Okay, for example, suppose we've seen this sentence in training. I have to make sure when I get home to feed the cat, but we've never seen the word dog after the words feed the. Oh, somebody forgot to do the backticks for the opening quotes in LaTeX. In our test set, we are trying to predict what comes after the prefix I forgot when I get home to feed the. And I'm going to take a... Is that too pedantic to send somebody a... No. No, I'll do it because I know I do that myself all the time. What page is this? 16. Page 16. Feed the opening quotes. Okay. In our test set, we are trying to predict what comes after the prefix I forgot when I got home to feed the. So this is our sort of our input, and we want to predict dog. An n-gram language model will predict cat, but not dog. But a neural language model, which can also make use of the fact that cat and dog have similar embeddings, will be able to assign a reasonably high probability to dog as well as cat, merely because they have similar vectors. Let's see how this works in practice. Let's assume we have an embedding dictionary E that gives us, for each word in our vocabulary V, the embedding for that word, perhaps pre-computed by an algorithm like Word2Vec from Chapter 6. Figure 7.2 shows a sketch of this simple feed-forward neural network language model, or FNM, with n equals 3. Sorry, it's FFNNLM. With n equals 3, where n here is the number of words. Yeah, the number of words given to us before we need to predict the output. We have a moving window at time t with an embedding vector representing each of the 3 previous words wt minus 1, wt minus 2, and wt minus 3. These 3 vectors are concatenated together to produce x, the input layer of a neural network, whose output is softmax with a probability distribution over the words. Kashunk says FNNNLM. FNNNN. No, I think FF because it's feed forward. Unless this is a joke that I don't get, which is also possible. Where was I? Oh, these 3 vectors are concatenated to produce X, the input layer of a neural network whose output is a softmax with a probability distribution over words. Known words, I guess we should say. Thus, Y42, the output of node 42, is the probability of the next word WT being V42, the vocabulary word with index 42. So we have an output node for every single word in our vocabulary, and we're going to take softmax over the predicted output words. The model shown in figure 7.12 is quite sufficient, assuming we learn the embedding separately by a method like the word2vec models of chapter 6. The method of using another algorithm to learn the embedding representations we use for input words is called pre-training. If these pre-trained embeddings are sufficient for your purposes, then this is all you need. But beware of genre effects. So if you have like web text like Twitter and you're trying to predict them using vectors trained on something like the Wall Street Journal corpus, you might get some kind of weird results because people don't talk the same way when they're writing for the Wall Street Journal as they do on Twitter. And that's my, I write a lot of reviews. Cashsunk says, no, you gotta write. Thumbs up. However, we'd often like to learn the embedding simultaneously with training the network. This is true when whatever task the network is designed for, sentiment classification or translation or parsing, places strong constraints on what makes a good representation. Let's therefore show an architecture that allows the embeddings to be learned. To do this, we'll add an extra layer to the network and propagate the error all the way back to the embedding vectors, starting with embeddings with random values and slowly moving towards sensible representations. So this is, it's not quite ensembling because it's a single model in terms of like backprop and updating, but it is doing multiple tasks at the same time. And I've seen also quite a bit of work here using things like federated learning. Is this where people use federated learning? I'm gonna look that up. Because it sounded right when I said it in my head, and I was like, yeah, that seems right. Nope, this is a way of doing learning. It's a way of distributing your compute. So yes, I'm sure people do use it for that, but that's not what I'm thinking of. Oh, maybe I'm thinking of multitask learning, where you learn both of them at the same time, but the outputs from the embeddings aren't immediately the inputs to the language model. Instead, you're doing two separate tasks that are sort of similar. So, like image captioning and something else that's like image captioning. I don't know. Sorry, that was just a tangent. I'm going on a wild hair. Blah, 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 blah. For this to work at the input layer, instead of pre-trained embeddings, we're going to represent each of the n previous words as a one-hot vector of length v, i.e. with one dimension for each word in the vocabulary. So you take your input text, and instead of having just a text string, you have a matrix where each column is a word that you have in your vocabulary. Each row is a word, and then for each word, your values are going to be 0 in all columns except the column for the row that it is, and there it'll be 1. And here is our perfectly adequate, is that what he said? They said? I don't know who wrote this bit. Way for doing neural language modeling if you have pre-trained in vectors. Pre-trained vectors. Oh my gosh, it's 10:07. Yeah, let's go through this diagram, and then I think I'm gonna call it a day because I think a meeting coming up that I should probably show up for, huh? Yeah. Yeah, so let's go through this diagram and then we'll call it a day. We spent a lot of time talking about how to pronounce D, aka day, aka del, but that's also delta and it's not delta, aka do. So this is the input layer. So this is our text that we're inputting. And because we're not training the embeddings, we don't have to do one-hot encoding. We just take the embeddings that we have from our pre-trained stuff. And The 35 there, I think, is probably the where this word is in the pre-trained embeddings. So it's like the 35th word. And then 9925 would be ground, and 45180 would be there, I think. And then 42 would be lived. So we take the embeddings that we have pre-trained, and then we pass those embeddings, which are vectors of the same dimension. So if you have a set of embeddings, it'll be like each word has 500 dimensions or 1,000 dimensions or 20 dimensions, or however they do, because it's a lower dimensional projection of a higher dimensional space, where the higher dimensional space is co-occurrence between all words. But if you don't project it down, then the dimensions of your space are the same as the size of your vocabulary, which if you're working with a language like English is extremely big, and that's not very memory efficient, and it is also very sparse. So when embedding is the projecting down into a more compact little nugget, I guess, your nugget data structures. And then we have some charmingly informal, I think Mary Berry would say, line showing the connections between each of these embeddings. So each node in each embedding is passed into each node of the hidden layer, and then the hidden layer is passed on to the output matrix, which is the same size as your vocabulary and gives you the probability. So I'm assuming we're going to do some sort of softmax here. Excuse me. The probability that the word is the probability the next word is from that word. Oh, and this is from The Hobbit, this example. And the text for this is a simplified view of a feed-forward neural language model, moving through a text. At each time step t, the network takes the next 3 context words. So the next one would be, instead of hole in the ground there, we would be ground there lived, a would be the next word. Converts each to a d-dimensional embedding and concatenates the 3 embeddings together to get a 1 times nd unit layer input x for the network. So we take our embeddings and we just make 1 flat layer here. These units are multiplied by a weight matrix W and a bias vector B, just like we've been talking about, and then an activation function to produce a hidden layer H, which is then multiplied by another weight matrix U. So you'd probably want to use ReLU or leaky ReLU there. For graphic simplicity, we don't show B in this and future pictures. Finally, a softmax, I was right, output layer predicts at each node I, the probability of the next word WT will be vocabulary word VI. The picture is simplified, but it's because it assumes we just look up in an embedding dictionary E, the d-dimensional embedding vector for each word, pre-computed by an algorithm like Word2Vec. So this is your basic neural language model idea. And we still haven't talked about training. No, that's not true. That's not true. We did talk about the way that loss is computed and the way that we update our model, which is using backpropagation, which is also known as something differentiation, partial differentiation, cross differentiation, which is an improvement over cross entropy, because cross entropy can only give you updates on the one previous layer, and backpropagation using the computational network graph, computation graph, sorry, not computational network graph. And this section, I'm trying to remember the exact words. This bit here, computation graph, yeah, using the computation graph and propagating back through, and then you guess the next thing, and then you propagate the error through, and you guess the next thing. We had a tiny little bit of practical advice about putting together networks and choices, which is this section on page 15, which I think is probably the most immediately practical bit of advice. And then we got a little bit into the actual language models. We talked about embeddings, and we talked about pre-trained embeddings, and then next time we will pick up with concurrently training embeddings and language models together. And this, so I mean, obviously for languages like English, you've got your pick of pre-trained embeddings, that's great. But if you're working with a language that doesn't have as much, NLP research done on it, you may not have the luxury of pre-trained embeddings. So you're going to have to, do more of the heavy lifting yourself. And that's not fair. And I agree. So if you are working with a language that has fewer pre-trained embeddings, that'll be useful for you guys. Yeah. Thanks for joining me. Oh, I'm starting to lose my voice a little bit. I think that is a good sign that it is time to wrap it up for today. Hopefully this was enjoyable. I'm sorry that I say math words bad, and thank you for teaching me how to say math words good. I found it very helpful for me personally, and hopefully other folks also found it helpful. And I will see you guys on Friday if you're joining for that, for live coding. I'm not 100% sure what I'm gonna do. Somebody mentioned it might be nice to talk about setting up a TensorFlow pipeline for the Quora insincere questions competition, but also I'm scared of competitions a little bit. I know I work for Kaggle. I know I'm still scared of competitions, but we'll find out. I'll let you guys know on Twitter, and I will see you on Friday. Have a great day.